Preserving humanity's knowledge. The memorialization of human knowledge has deteriorated even as human knowledge has advanced. The oldest records beyond simple symbolism of which we are aware are imprinted on ceramic tablets. To this date, these remain representations of the most resilient means to comprehensively secure information. Subsequent technologies such as ink on a variety of media, and even more so recent optical, electric, or magnetic storage technologies, cannot match their longevity. These later technologies are frighteningly ephemeral by themselves or in their regular environments and susceptible to destruction by temperature, chemical, electromagnetic, radiation, mechanical, and even biological interferences. All of them require regular maintenance. But even such maintenance cannot keep them from long-term deterioration. They will eventually require restoration, replication, or transfer to another medium. Further, even well-secured records in such media cannot be completely saved from cataclysms, accidents, or willful destruction. There does not seem to be an absolutely secure technology to guarantee the survival of records. Even ceramic materials can be destroyed by a variety of creeping and sudden influences. Moreover, the idea of reverting to ceramic data recording may strike many as strange. However, we should not be repelled by the shortcomings of ancient ceramic record-keeping technology. Ceramic science has come a long way since its beginnings in the firing of natural clay. Its applications in a great variety of industries are of growing, monumental importance. The prevalent ingredient of clay tablets, the metalloid element silicon, has remained in many ceramics. But modern ceramic composites can be drawn much thinner and can be made vastly more resistant to damage. That silicon is also the most widely used basic integrated circuit material is a coincidence whose great potential must be explored. Ceramic composites, many of which we might describe as glass, have already found application in a wide variety of information technologies, including optical fibers, integrated circuits, LEDs, screens, and insulators. One of them, silicon carbide, exhibits extraordinarily useful optical and electrical properties as well as remarkable resistance to external degradation. Another ceramic, boron carbide, does not lend itself to comparable optical or electrical applications. But it is an even harder material that provides stellar impact and radiation shielding, making it ideal for casings. Applications of these and other ceramic composites remain to be investigated. We may consider metals as alternative media. However, the resilience of metal-based materials and particularly data recording technologies available or foreseeable today lags behind the possibilities of ceramics. Moreover, approaching the resilience of ceramics would require precious metals of which we do not possess sufficient amounts or the cost of which would be prohibitive. Conversely, there is a virtually endless supply of silicon and carbon on Earth. Even boron could be sourced in sufficient quantities, although it is not nearly as ubiquitous. Partner elements to create viable long-term electronic storage devices are not needed in vast quantities. This makes ceramic material relatively inexpensive once technological impediments to its application are solved. It is also an apt medium for information storage technology. Vast amounts of information can be stored in minuscule etchings or moldings, in embedded hardened integrated circuits, or in other molecular implants or manipulations of an amorphous or crystalline substrate. For better durability, data storage technology may go beyond traditional layouts to cube or spherical designs. Much of this technology remains to be developed. However, it is already visible that such technologies can match or exceed the storage potential of metal or traditional metalloid media. But most importantly, their extraordinary resilience potential makes them the technology of choice for the long-term preservation of information. Nevertheless, not much research and development has been spent on ceramic information storage, or any long-term record-keeping for that matter. Nor does there seem to be sufficient demand to warrant much effort in that area. We seem to trust that keeping information in backup repositories not substantially different from the original storage media is adequate. Nor do we spend much time to defend against the deterioration and destruction of other components of information systems that can retrieve and distribute stored information. Their complex nature makes them even more prone to failure than storage media. The same or related ceramic technologies applicable to data storage might be applied to data retrieval and distribution. Yet, currently, the hardening of information systems against natural or human interferences mostly consists of incremental reinforcements or duplications of existing, fundamentally susceptible technologies. Few seem to notice how precarious humanity's dependence on insufficiently secured information systems has become, placing us all in existential danger. Spectres of mischief, terrorism, war, natural disasters, human error, or more comprehensive doomsday scenarios should motivate us to safeguard our information, as well as the systems on which we rely to apply that information, against all reasonably possible threats. Even relatively limited disturbances may lead to substantial disruptions or a collapse of information-based existences. Limited disturbances may be overcome rather easily by multiplication and spread of data sites and by mobile data processing infrastructure. However, we may be foolish to gamble the development level, well-being, and possibly the survival of many humans and humanity as a whole on the hope that there will not be more comprehensive challenges to our information systems. Even if things continue to progress in an unspectacular manner, our systemic failure to sufficiently secure information increasingly exposes humanity to disastrous setbacks. A more lasting information system is not only required to halt the deterioration and other destruction of information generated before the electronic age. The particular susceptibility of electronic storage media and application appliances makes a more lasting data system obligatory if we want to keep adequate access to information generated during that age. An additional reason is the rapid obsolescence of storage media and application systems. Unless we transfer information from older to new systems, the information stored on older systems becomes difficult and eventually impossible to retrieve. Such transfers constitute rising challenges with increasing amounts of information and may not be undertaken fastidiously enough when new systems are introduced. We may rely on the continued functioning of old information systems. However, their repair or replacement according to superseded technologies may become increasingly difficult. Thus, much of our electronically generated information may fade away even before more historical records. As a consequence, humanity would lose an understanding of its recent history, adding to the challenges of incomplete records dating farther back. This poses problems that exceed a mere inability to satisfy general curiosity by future generations regarding the past or the disappointment of prior generations that little or no evidence of their existence will remain. They also go beyond the inability of historians and other scientists to analyze and draw conclusions from human development. Much more critical problems may arise from a lack of historical information if humans should lose the ability to continue technology on the level of then currently documented and implemented technology, or if they would want to revert to former technologies or consult specific historical information for other practical reasons. Considering these potential and impending issues, the development and broad application of a lasting data storage, retrieval, and distribution system are thus desperately needed. Every day such a system is not in place unnecessarily imperils human well-being and possibly survival. If we failed to act, future generations would look at us in disbelief and scorn for not having anticipated the great danger of information oblivion for ourselves and them. The question is then who will take on this undertaking? The first step would have to be the development of a common normative setting based on existing and anticipated technologies. Companies already active in research, development, and manufacture of ceramics and their applications in combination with enterprises that focus on storage, retrieval, and distribution technologies would be an obvious choice. The implementation of the resulting system might be left to current generators, holders, accumulators, organizers, and access providers of information. However, the number of those may be so great that locating appropriate records when they are needed in the described scenarios may be difficult or impossible. This suggests an additional congregation of essential information in central repositories that are hardened against interference. Parallel administration of a number of such information vaults may be indicated as yet another security measure. To serve their purposes, these would not only have to contain information, but also hardware to access and distribute such information. Ideally, all parts of an information system might be integrated into one unit, including its power supply. This would at once simplify and further harden information preservation devices. To continue data preservation without unnecessary interruptions, information vaults might include facilities to produce storage, access, and distribution hardware, or at least a sufficient supply of free storage capacity. They would also have to contain cataloging and search facilities for the extensive information they store. Further, they would have to provide information in a manner that can be accessed by humans in various states of development. In this context, one would have to consider that future generations might suffer a deterioration of technological skills, advance to alternate technologies, and not understand recorded languages or terms in such languages. Special provisions to ease access for them, such as training and universal symbolism at least in the initial directions, would have to be arranged if a long-term assistance to humanity were taken seriously. Finally, directories regarding the whereabouts of these repositories would have to be distributed in a way that survives deteriorative and destructive eventualities. Among these eventualities would have to stand that humans accessing such repositories would cause intentional or unintentional damage. A combination of information repositories with more imminently needed practical provisions for human survival may seem indicated. However, such a combination bears dangers because humans desperate for immediate supplies may neglect or even destroy the indirect assistance facilities of information systems and use them or their housings for other purposes. It is also conceivable that forces would emerge that wish to withhold historical knowledge from certain groups or all humans. It seems impossible to foreclose all possibilities of intelligent interference. Such measures may also make access difficult at times when access to information vaults is needed most. But at least some repositories may be safeguarded in ways that only afford higher developed levels of humanity with access. Clues might be hidden in locations or in codes that only higher levels of civilization would be able to find or decode. Additional safeguards may be built in by cooperation requirements. Some repositories might be placed beyond Earth, which would also add to their safety generally. Codes might be hidden in monumental arrangements that require technological sophistication to understand but upon its attainment become undeniable. One might also consider implanting mapping code into smaller objects that higher evolved levels of humanity are bound to study. The DNAs of humans or particularly resistant organisms with broad distribution might be appropriate carriers. Natural and artificial organisms could be programmed to build silicon or other lasting structures that carry mapping and even substantive information. If prior iterations of human civilization of which we are unaware or to which legends point existed, those would also be the logical places for us to search for information forgotten civilizations would have left us. The lengths to which we go to secure information and humanity may be debatable, and we may not have the will or means to implement all that is possible. However, we must do dramatically more than we have so far if we want to avoid tragedy.